this is S. Lakshmanachari, working as Assistant Professor in Department of Cyber Security, Institute of Aeronautical Engineering, Hyderabad. In this lecture, we are going to discuss decimal arithmetic unit. So, in a digital computer system, we have three main functional parts that are central processing unit, memory, and I/O subsystem. So these are the three main important functional parts. Okay, so the user of the computer prepares the data in decimal and it processes the input decimal numbers and it generates the results in the decimal number. So the CPU with ALU, it performs the various arithmetic and logical operations on the binary numbers. So it will perform on binary number. Okay. So, but if the CPU with ALU wants to perform with decimal numbers, then the decimal numbers first it needs to be converted into the binary numbers. Then we will perform the operation, and then the results will be converted into the converted from the binary numbers into the decimal. Okay, so that is a process. So, but this might be an efficient method when in applications requiring large number of calculations and a smaller amount of input and output data. But in some applications requiring lesser number of calculations and larger number of input and output data, this method might be inefficient. Okay, so in order to overcome that, we have to design the CPU. Using the decimal arithmetic unit. That means the decimal arithmetic unit, it can support the decimal numbers directly. That means it will process various operations directly with the decimal numbers. Okay, so a decimal arithmetic unit is a digital function that performs decimal micro operations. So this decimal arithmetic unit, it performs various operations directly with the decimal number. Okay, so it can add or subtract decimal numbers, usually by forming nines or tens complement of the subtrahend. So the computers capable of performing decimal arithmetic must store the decimal data in binary coded form. The decimal numbers are then applied to the decimal arithmetic unit capable of executing decimal arithmetic micro operations. So the unit, it accepts the coded decimal numbers and generate the results in the same adopted binary code. A single stage decimal arithmetic unit, it consists of 9 binary input variables and 5 binary output variables. So it is having 9 binary input variables and 5 binary outputs. So what are the 9 binary inputs? So here we are considering two numbers. Let us assume A and B. So A is represented using a 4-bit number. It is also B also a 4-bit number. So 4 plus 4, 8. We are considering some input carry also. It is a 1-bit. So total, see how many inputs. So this is one input and this is another input. Here 4 bits and one input carry, 1 bit. So total it is having 9 input variables and 5 output variables. So these are the sum values, S0, S1, S2, S3 and 1 output carry, C out. So this is 1. This is 4 bits. So total 5. So a single decimal arithmetic unit, it consists of 9 binary input variables and 5 binary output variables. since the minimum of 4 bits is required to represent the each coded decimal digit. So the electronic calculators invariably use an internal decimal arithmetic unit, since inputs and outputs are frequent. So inputs and outputs are decimal numbers. Because if you consider a digital electronic calculator, so with the calculator, we are directly performing some certain operations on the decimal numbers, because we are giving the decimal numbers directly to the calculator. Then it will perform some operation like addition, multiplication, division, subtraction. So like that, it performs some arithmetic operations, and finally it is giving the results directly in the form of decimal numbers. Okay, so that means here no need of converting the numbers from one form to the another form. Okay, so that's why we have to design the CPU in such a way that it supports the decimal numbers also directly. So the decimal arithmetic unit is a digital function that performs the decimal micro operations. So using this decimal arithmetic unit, we can perform two operations, that are addition and the subtraction. So the addition operation is performed with BCD adder. Similarly, the subtraction is performed with the BCD subtractor. So here the BCD, it stands for binary coded decimal. So BCD, it is a full form. So the full form of the BCD is the binary coded decimal. So let's brief look at what the BCD is. So in this code, each BCD, each decimal digit, so 0 to 9, is represented by a 4-bit binary number. So 0 to, so in general, the 0 to 9 are the numbers, are the digital numbers we are considering. So in this, every decimal number, it is represented by a 4-bit binary number. Suppose if you have a 0, so this 0 in decimal, so this is a decimal number. So this decimal 0, it is represented with a 4-bit binary number. It is a binary number. Similarly, 1, we can represent it with a 0, 0, 0, 1. So like that, 9. So 0 to 9 are the decimal numbers. So 9 we can represent it with 1, 0, 0, 1. So this is a representation of the all the decimal numbers in a 4-bit binary form. Suppose if you consider a 374 decimal number. So in this decimal number, every digit of the decimal number, it is represented with a 4-bit binary number. Okay, and it is a positional weights are 8421. So in the 8421 code, we are representing the every digit of the decimal number. So here you can see how we can write all the decimal numbers in a 4-bit binary number. So suppose if you have a 0, it can be represented in a positional weight 8421. So we can write 0, 0, 0, 0. Similarly 1. So we can write 0, 0, 0, 1. 5 we can represent 0, 1, 0, 1. Because by adding these positions, it will give its value. So 4 plus 1. So that is equal to 5. So that's why the corresponding bits will be, we have to make it once. So like that, we can write all the decimal numbers in corresponding 4-bit binary number. So the numbers from 0 to 9 are considered as the valid BCD numbers. And so here total we are representing with a 4-bit. So 4-bit means 2 power 4. So that means total we have 16 numbers. 16 numbers. So 0 to 15. So 0 to 9 are the valid BCD numbers. and 10 to 15 are the invalid BCD numbers. So these are the invalid BCD numbers. Okay, so because the 10 we cannot represent. Okay, because in 10 BCD form, how we will write? So 1 0 0 0 0, because here this 0, it is represented in a 4-bit binary number. So how we can represent 0? So 0 corresponding 4-bit binary number is a 0 0 0 0. So this one. Similarly 1. So how 1 can be represented? So 0 0 0 1. So in this way we can represent the BCD number. Okay, so far we have discussed and understood the BCD or 8421 code. Let us now look at the BCD addition. So how we can add any two BCD numbers. Okay, so for that we have to follow some certain rules here. Okay, so in BCD addition we have to deal with the three cases. So here we have to deal with three cases. The first case is after adding any two BCD numbers, if the sum is less than or is equal to 9 and the final carry is equal to 0, then the obtained result is correct. That is the first case. In the second case, if the sum value is less than or is equal to 9 and the final carry is equal to 1, then the obtained result is incorrect. Then we have to make it correct. So by adding 6, so we are adding 6 to that result, so that we can get the correct result. And the third case, is if the sum value is greater than 9 and the final carry is equal to 0. So in the third case also we will get the incorrect answer. So in order to get the correct answer, we have to add 6 to that result, so that we will get the correct BCD answer. Okay, so here you might have a doubt that why we should add 6. So because here the invalid BCD numbers, so invalid BCD numbers are 6, that are from 10 to 15. So these are the invalid BCD numbers. So we have to get the correct answer. We have to add this 6 to the result, so that we will get the correct value. Okay, let's see the BCD adder. So the digital system, it handles the decimal number in the form of binary coded decimal numbers. So a BCD adder circuit adds two BCD digits and returns a BCD sum digit. The BCD numbers use the digits ranging from 0 to 9, which are represented in binary from 00000 to 1001. So all zeros, it represents a number, a decimal number 0, and 1001, it represents a decimal number 9. So the decimal numbers are from 0 to 9. Each BCD digit, it is represented with a 4-bit binary number. So consider the arithmetic addition of the two decimal digits in BCD together with a possible carry from previous stage. So in order to understand, let's consider a BCD numbers. So since each input digit doesn't exceed 9, because here in the decimal numbers the maximum number is the 9. So if you add any two numbers, like A and B, the maximum number of the maximum number is 9 and the minimum number is the 0. So and the output sum cannot be greater than 9 plus 9 plus 1. That means if you add all those, you will get the 19, because the maximum number is the 9 for a single digit. For another number also, the maximum number is the 9. And also there may be a chance of getting the input carry. If the input carry is also 1, then the 9 plus 9 plus 1. So total 19. So 19 is the maximum sum we can get using the BCD adder. So suppose that if we apply two BCD digits to the 4-bit binary adder, the adder will perform the sum in binary and produces a result that may range from 0 to 19. So here you can see a 4-bit BCD adder. So we have two numbers A and B. So for the A number, the minimum number is the 0 and the maximum number is the 9. Similarly for B number also, the minimum number is the 0 and the maximum number is the 9. And there may be a chance of getting the input carry. So the input carry, it may be either 0 or 1. So the maximum value for the input carry is 1. So at any point of time, the maximum sum output. So these are the sum output. So the maximum sum output will be 19. So that means 9 plus 9 plus 1 input carry. So total you may get 19 as the final output. So as a result, in order to build a BCD adder circuit, you will need a 4-bit binary adder for initial addition, logic circuit to detect sum greater than 9 or not, and one more 4-bit adder to add 6. Suppose if after adding any two BCD numbers, if the sum is if the sum is more than 9, then we have to add 6 to that, so that we will get the correct BCD answer. So here you can see the derivation of the BCD adder. So it is a BCD sum and it is a binary sum. Okay. So here the decimal numbers are represented. So the decimal numbers are from 0 to 9. So these are the valid BCD numbers. And from 10 to 19 are the invalid BCD numbers. These are the valid BCD numbers. So the representation of the decimal numbers from 0 to 9 is same in BCD form and the binary form. Suppose if you have a 0, so the 0 is represented with all the zeros with the carry 0. Similarly, the same decimal 0, it is represented in the binary sum 0, 0, 0, 0 with the carry k0. So this representation is the same in both the BCD sum and the binary sum from decimal number 0 to decimal number 9. But this after the numbers from the number 10 to 19, the representation will be different. Suppose if you consider a 10, so 10 in BCD form we can represent 0, 0, 0, 0 with the carry equal to 1. So the 10 we will represent like this in BCD form. But in the binary form, the 10 will be represented with 1, 0, 1, 0 with the carry 0. So that means if you compare the representation of the binary sum and the BCD sum, there is some differences are there. Okay, so that's why the numbers from 10 to 19 are considered as invalid BCD numbers. Okay, so the only correction is needed in the second half of the table. Because from 0 to 9 the representation is same in both the binary sum and the BCD sum. Only the second part. So second part means from 10 to 19 is the different. So that's why we have to concentrate on that the decimal numbers from the numbers from 10 to 19. So the minimum sum we can obtain from the 4-bit adder is 0 and the maximum sum is the 9. So the table shows that when the binary sum has an output carry k equal to 1, the correction is needed. Okay, so in binary sum, suppose if you see a binary sum, if k is equal to 1, then the output will require a correction. Okay, so first condition is k, output carry is equal to 1, which covers the numbers from 16 to 19. So k is equal to 1. So k is equal to 1 here. So what are the numbers from 16 to 19? 16 to 19. So here you can see. So k is equal to 1. So that numbers are from 16 to 19, which requires the correction. Okay, so this is the first condition. Coming to the second condition, the remaining 6, so total we have 10 to 11, 10 to 19. So 10 to 19 it requires correction. So already the 16 to 19 covered in the first condition. And the remaining cases are the remaining 6 combinations. So the remaining are 6 combinations or 10 to 15 requires correction with the bit on the Z8 position set to the 1. So if the Z8 position set to 1, see Z8 position set to 1. Okay. So if we closely look at the table, 2 unrequired cases, 8 and 9. Okay, so see here. So if the Z8 is set to 1, here these 2 cases, that means 8 and 9 also covered. But the 8 and 9 are valid BCD numbers. So that's why this Z8 we are also combining with the Z4. So this 4. So we have considered this, we are considering Z8 along with the Z4. So that the numbers from 12, 13, 14, 15 covered. So here in the second case, 12, 13, 14, 15 covered by taking Z8, Z4 is equal to 1. And remaining 10, 11 are there. So this 10 and 11 will cover by taking Z8, Z2 is equal to 1. So in this way, all the numbers from 10 to 19 will be covered. So the expression is C is equal to K plus Z8, Z4 plus Z8, Z2 will be the Boolean expression for the adder circuit. Okay, so that means C here. So K is directly covered from 16 to 19. Okay, so 12 to 15 will be covered by Z8, Z4. So Z8, Z4. So 12 to 15. So this is 12 to 15 is it is a representation. So all ones using K map it is equal to. So this will be represented with Z8, Z4. Okay, and the remaining 10, 11, 10 to 11. So this will be covered using Z8 into Z2. So 10 to 11. So these are the 10 to 11. So by taking this quad, okay, so by taking this 4 bits nibble, then it will form a Z8, Z2. Okay, so now we are combining all these cases. So C is equal to K plus Z8, Z4 plus Z8, Z2. So if the C is equal to, so if this expression it gives 1, it requires that we need to add 6 to that result, so that we will get the correct BCD answer. So here you can see the BCD block diagram of the BCD adder. So here in this we are using a 2 4-bit binary numbers. So this is a first 4-bit binary adder, and this is a second 4-bit binary adder. So already we know for every BCD adder it is having 9 input variables and 5 output variables. So 9 input variables are AND bits, added bits, and input carry. So input carry is a 1 bit, and we are considering a 4-bit number. So AND bits are 4, added bits are 4. So total 9 inputs and 5 outputs. So this is a C out. This is a carry, output carry. This is our output carry. Okay. Next, 4 outputs: Z1, Z2, Z4, Z8. So these are the 4 outputs, some outputs. So total 5 outputs are there. So see here. So this added bits and AND bits. So added means the number which we are adding to the another number, that is called added bits. So this we are adding with this. Let us assume this is number A and this is a B. So we are adding. Let assume this is A and this is a B. So that means we are performing A plus B. So that means the B number we are adding with the number A. So in this, the A, B bits are called added bits and A bits are called AND bits. Okay. So after adding these two numbers A and B, then it will produce a sum. So that is Z1, Z2, Z4, Z8. So that will be given to the second 4-bit binary adder as AND bits. Okay. And see here. So here we are generating the output carry with the help of some combinational logic circuits. We are using one XOR gate and 2 NAND gates. So this is the first NAND gate and this is the second AND gate. This is the first AND gate. This is the second AND gate. This is the first OR gate. Okay. So output is given to the OR gate, and outputs of the AND gates also given to the OR gate. So finally we will get the output carry. Okay. And see here. Suppose if the result, so see here, so 0. So that means if the sum is greater than 9, greater than or is equal to 9, then we have to add 6. Okay, now. So that's why we are adding 6 here. So if the Cout is equal to 1, so what Cout is equal to 1, it indicates that the sum is greater than or is equal to 9. So when we are adding 6, if the sum is greater than or is equal to 9, in that case we have to add 6 to that result. Okay. So 6 means how we can represent 0, 1, 1, 0. So that's why the first bit is represented. So 0, we are loading with 0, first bit, and last bit. And Cout is equal to 1. So this Cout will be given to the second and third bit. So 1, 1. So that means total, by combining all these bits, it will be considered as a 6. So this 6 we are adding with this one, AND bits. Okay. Okay. So see here. Suppose if you add, suppose if you consider a number, if you consider a number 5 and 5. Okay. Otherwise 5 plus 4. Consider a number 5 plus 4. So B is equal to 4 and A is equal to 4. So 5 plus 4. So what you will get? 9. So what is the condition? If the sum value is greater than or is equal to 9. So 9. So that means 1, 0, 0, 1. So now our sum is the 9. So it generates a carry 1. So here it doesn't have any carry generated because 5 plus 4 9. It doesn't generate any carry. So C out is equal to 0. Now it is 1. It is 0. Here also 0. Here see 1. Here 1 0. So the output of the AND gate also 0. See. So in this case 5 plus 4 9. Okay, 5 plus 4 9. So in this case here the sum value is 9. Oh, okay. So here we are adding 6 only if the sum value is greater than 9. Greater than 9. Okay. So if we are adding 6 only if the sum is greater than 9. But here the sum is 9. So no need of adding 6. So that's why here in this case C out will be 0. So that means here we are adding all zeros. So if you are adding all zeros to the 1001, finally you will get the same number 1001. So that is equal to 9. So 5 plus 4 9. So we got the correct answer. But if you consider a 5 plus 5, so see here, consider the another number. So consider the another number 5 plus 5. Okay. So 5 plus 5, what you will get? You will get 1 0 1 0 as the sum. So here one carry is generated because 5 plus 5. Okay. So here carry is a 0. So what is the output of the first AND gate? Here 1, here 0. So 0. And here 1, here 1. So here output of the second AND gate is 1. So now all this 0, 0, 1 we have given to the OR gate. So what is the output of the OR gate? It is equal to 1. That means right now the sum is 10. It is greater than 9. So that's why we need to add 6 to that result. Okay. So 6 means 0, 1, 1. 6 means 0, 1, 1, 0. This we are adding with 1, 0, 1, 0. Okay. So see here 1, 0, 1, 0. So this is a 10 equivalent. We are adding 6. 0, 1, 1, 0. So 0, 0, 0, 0, 1. Okay. So that means sum we have given 0. Here it is a carry. So this carry it indicates that the result is greater than 9. So how we are representing 10 in BCD form? 10, 0, 0, 0, 0. So it is the actual representation of the BCD number. So in this way, the BCD adder will add any two BCD numbers. Okay, so we will use a 4-bit binary adder as an example, which accepts added and AND bits as input and the carry input as the input carry. And it has 5 outputs: Z8, Z4, Z2, Z1 and K. And the logical circuits is designed to identify the Cout using the output carry K, and Z8, Z4, Z2, Z1 are outputs. And coming to the subtraction, so just before we have seen how we can perform the BCD addition. Now we are discussing the BCD subtraction. So generally the two BCD numbers are subtracted by adding the 9's complement of the second number to the first number. So let's see the BCD subtraction using 9's complement numbers and BCD subtraction process using it. So 9's complement. So how we can find the 9's complement of a number? So we can find the 9's complement of a number by subtracting that number from the 9. Suppose if we want to find the 9's complement of the 0, so that means we have to subtract this number from the 9. So 9 minus 0, so 9. So 9 is the 9's complement of the 0. And 1. What is the 9's complement of the 1? So already we have seen. So 9's complement of the 0 is 9. 9's complement of 1. So that means 9 minus 1, 8. So in this way, we can find all the 9's complement of the given number. And coming to see the 9's complement of the 9. So 9 minus 9, so 0. So in this way, we can find out all the 9's complement of the corresponding numbers. So in order to find the 9's complement, we have two approaches. In the first approach, we have to complement the given number, then add 1010 to the complemented number, so that we will get the 9's complement of the number. Let's see, consider a 5. Consider a number 5. It is represented in 0101. What is the 9's complement of the 5? 9 minus 5. 4. We have to get the 4. Let's see. So in this first approach, we have to complement the given number. So what is the given number? 0101. We have to complement that first. So after complementing, we will get 1010. For that number, we have to add 1010. So we have added 1010. So you will get 0100 along with the carry. So in the first approach, if any carry is generated, then we can neglect that. We have to ignore. So 0100. So that is equal to 4. So we got the 9's complement of the 5. So answer is the 4. And coming to the second approach. So here in the second approach, we have to add 6. That means 0110 to the binary number, then complement the number. So consider the number 5, 0101. So in the second approach, first step is we have to add the 6. Okay. So given number is 0101. For that number, I am adding 6, 0110. So I got 1011. Okay. So that result we have to complement. Okay. The result we have to complement in order to get the 9's complemented value. So after complementing, what you will get? 0100. So that means 4. So 9's complement of the 5, 4. So we got the correct answer. So in this way, the BCD subtraction will be performed. And here consider a one stage of decimal arithmetic unit. Decimal arithmetic unit. Okay, so using this decimal arithmetic unit, we can perform either BCD addition or BCD subtraction. So this is a mode bit. This is a mode bit. So using this mode bit, we can perform the addition. Using this mode bit, we can specify whether we are performing BCD addition or BCD subtraction. So when m is equal to 0, it performs addition. When m is equal to 1, it performs subtraction. So suppose if we are performing addition, so the m will be 0, and that 0, okay, so m will be 0 for addition. Let us assume this is a b. So when m is equal to 0, then the addend bits will be directly given to the BCD add without performing the 9's complement. Then that number b will be added with a. Then we will get the sum as the output. Okay, so that is the addition. Suppose if you want to perform the BCD subtraction, then this BCD then the mode bit will be set to 1. So if mode bit is set to 1, then the added bits will be, we are performing a 9's complemented. That means this bits will be performed by 9's complement will be performed. After 9's complementing, that 9's complement value will be given to the BCD adder as one of the input. And already we have a AND bits. So this 9's complemented bits are added with this AND number. So in this BCD subtraction, mode bit 1 also will be given to the input carry. Okay, so that means here we are performing, see, this is a number and this is a B number. A plus 9's complement of B. So what is so we are performing subtraction here. A minus B. So that means here A plus 9's complement of B plus 1. So that is equal to A minus B. That means that is equal to. So here after performing 9's complement, then we are adding with A and we are adding 1 with the input carry 1. Because the mode bit is equal to 1. That mode bit will be connected to the input carry. So that it performs A plus 9's complement of B plus 1. It gives a subtraction. It performs a subtraction operation. That means the contents of the B is subtracted from the A. Okay. So in this way we can perform the BCD addition and the subtraction. So see here. So here this is a decimal number 0 and these are the added bits and these are the 9's complemented of that particular number. So here see. So x1, x2, x3, x4, these are the 9's complemented of the B values. Suppose if the B values is 0, 0, 0, 0, 0, so that means 0. What is the 9's complement of 0? 9 minus 0, 9. So 1, 0, 0, 1. So this corresponding to 9. Suppose if you consider a 4. So how we can represent 4? 0, 1, 0, 0. What is the 9's complement of the 4? 9 minus 4, 5. So 0, 1, 0, 1. So it is corresponding to 5. So in this way we can find out all the 9's complements. And you can get the Boolean functions. You can get the Boolean function. Suppose if you compare x1 and b1, so how we can relate? So x1, the first bit is 1, here 0, here 0, here 1. That means x1 is equal to b1 bar. That means complementing. x1 is the complement of the b1. Next, if you compare x2, b2, so these values, so x2 and b2 both are same. So x2 is equal to b2. Next, x4. So it is a XOR operation of b4 and b2. So if you perform XOR operation of b4 and b2, it results in x4. And x8. x8 is a performing AND operation on the complement of b8, b4, b2. So it gives a x8 value. Okay. So in this lecture we have discussed about the BCD numbers, binary coded numbers, and also we have seen how to perform the BCD addition and BCD subtraction, and finally we have seen one stage decimal arithmetic unit. So using that decimal arithmetic unit, we can perform either BCD addition or BCD subtraction. That means using a single circuit, it is able to perform both the addition as well as subtraction. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.